If we review all of the relationships between pressure, volume, temperature, and amount that we discussed in our last video, we would have pressure is directly proportional to amount and to temperature. Volume is the same. It's also directly proportional to amount and to temperature. As volume goes down, pressure goes up, so pressure and volume are inversely proportional. These relationships cover 4 physical laws: Avogadro's, Gay-Lussac, Boyle, and Charles. Or should it be Charles-Boyle?
God, it just sounds right that way.
Which show us that pressure and volume are related to amount and temperature. But a quick analysis of the units show us that they can't be equal to each other. On the one side we have Pascal times meters cubed, and on the other we have moles Kelvin. Pascal is a derived unit, so let's put it back into our base SI units. The meter in the denominator cancels, and we get kilograms times meter squared divided by second squared, which still don't equal moles Kelvin. But 1 kilogram meter squared per second squared is equal to 1 joule. As we said, thermodynamics is all about tracking and quantifying energy, and here we have our unit for energy. Moles Kelvin is not a unit for energy, so the piece we're missing to bring all the pieces together into an equation has to have units of energy per mole Kelvin. You could think of this as the energy it takes to raise 1 mole of a substance by 1 Kelvin, or the maximum amount of work you could get from 1 Kelvin of 1 mole of some substance. Such a factor was already known for individual particles, Boltzmann's constant. To get Boltzmann's constant into moles, we only need to multiply it by Avogadro's number to get 8.314 joules per mole Kelvin. This is called the ideal gas constant, and it's the missing piece that completes the ideal gas law. PV equals nRT. Pressure multiplied by volume is equal to the moles of gas times the absolute temperature multiplied by a proportionality constant to tie it all together. You're going to find that ideal gas law questions don't always present themselves using SI units. It's more common to find temperatures recorded in Celsius, for example, though it must always be converted to Kelvin for use in thermodynamics. Because Kelvin and Celsius increments are the same size, the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. And different applications record pressure in a variety of units, such as atmospheres, or bar, or millimeters of mercury. And for volume, liters are often more convenient than cubic meters. These alternative units for pressure and volume are perfectly acceptable to use in the ideal gas equation, but you have to be sure to use the corresponding units of R. We'll use the ideal gas law in some practice problems and discuss the limits of the ideal gas law in our next video.